Okay, this screencast, I'm going to go over these problems for our first semester exam review for AP Stat. So the first one, we actually haven't seen one quite like this, but it's very similar to the type we've done, and I thought y'all could handle it. We studied some null hypothesis problems, and so in a certain county, newspaper reports the average family income in the county is $45,000. First-time homebuyers believe the average income is less than reported. Which of the following hypotheses be appropriate? And so when you see 45,000, that's going to be our average there. Instead of a p-value, this is going to be a mean. But it's the same idea that we've done. So obviously one of these would be our null hypothesis. And then it's just a matter of figuring out when it says is less than reported. So less than, you would have to, your alternate hypothesis would be less than. And so you've got it. Again, we haven't seen a mean before, but we'll see them pretty soon. And I thought it reviewed the same basic concept. Typically, we're going to see p equals and p less than or p greater than or p not equal to on the final exam. Yeah, we have seen problems like this. And so the first thing, well, let me just adjust the, so you can see that a little better, sorry. Okay, so the weights of a box of cereal are normally distributed. We have some normal distributions here with a mean of 14.1. That's most of these are centered somewhere around there. And a standard deviation of 0.04. Probability of selecting a box with at least the advertised weight of 14 ounces. So there's a couple things there that you should notice. At least means we're going to shade greater than here. So it's going to be greater than. So this one's shading the wrong direction. Can't be that one. Greater than could be this one. Greater than could be this one. Not this. That shades to the left. And it could be that one. So we've eliminated maybe two of the answers so far. And then it says 14 ounces is the value we're checking. So that's about 14 there. Here we're at 14 point something there, so that's not the right value there. And 14. What I don't like about this one is the mean doesn't seem to be 14.1. 14.1 would be somewhere in here. And so the mean isn't in the right spot, so that one can't be it. So we've eliminated pretty much everything except for A, which is 14 and to the right. Therefore, there you go. Here you go. The following box plot summarizes two data sets. It's been a while since we've seen a box plot, and so I thought this would be good to go over because we have some questions on box plots. Set X and Y, set X and set Y have the same number of data points. Well, from a box plot, you really can't tell how many data points, so I'm going to say false on that one. Set X contains more data points than set Y. Again, we don't know how many data points, so that's just obviously false. The data in set X have a larger range than the data in set Y. So the range is the max minus the min is the range. It's just a value. The value of this minus this is quite large, but here there's an outlier here. That seems to be about the same distance here, so it looks like pretty much the same range. So I would not say it's larger. Let's look at the last one. The median of set X is less than the median of set Y. Well, here's the median of set X, and here's the median of set Y. It looks like Y is less than X, so that seems to be false. Let's see why this is true. About 50% of the values in set X are greater than 75% of the values in Y. Now remember where box plot works. This line here, this is 25% of the data, the upper 25%. This is the next 25% between here and here, right? And then there's 25% of the data, exactly 25% of the data here, and then 25% of the data here. Same thing over here. We've got 25, we've got 25, We get 25 and 25 here. 25 obviously includes all of that there. So it says this, about 50% of the data values in set X, that would be, let's see, 50% of the data values, that's this 50% right here, are greater than about 75%. Those are bigger than 75% of that. Yeah, that's true. So D would be the correct answer. And that's what the book said. Here we go. The number of T-shirts in a school sells monthly, store sells monthly, has the following probability distributions. So we have these probability distributions. This is the idea of expected value. And so we say the expected value, use a big E for this, of this is going to be, and so we start multiplying, right? We get, actually first we want to figure out the number of shirts here. And so we go 0 times 0.02 plus, we're basically taking each of these number of t-shirts times the probability of getting that t-shirt, of making that t-shirt, or selling that t-shirt I should say, 1 times 0.15 plus, again we're just going to go down the line and add all of these up until we get to 10 times 0.05. Add all those up, we're going to get the number of t-shirts sold. That's the number of shirts that are sold. It's not really exactly what we were looking for. We really want to figure out how much profit we're going to make, but we need the number of shirts sold. We need that number to get that. So to get the profit, each shirt sells for $10, but it costs $4 to make, so it's 10 minus 4 is $6 profit on each shirt. So if I take this number and multiply it by 6, I should get my answer. And I'm not going to bother to do all the work, but if you add that up, you get 3.78 for the number of shirts. And then you multiply that by $6 profit, and you get a total of 22.68. So the correct answer was C there. Population is strongly skewed right. So we have this big population skewed right here. For the sampling distribution with means of sample size 5. Now remember 5 is kind of small. 30 or bigger, we're just going, it's sampling distribution, that idea. It's going to be approaching normal or pretty much normal by that point. 5 is pretty small. So what's true? Well, according to the central limit theorem, the mean of the sampling distribution, I guess this would be x bar, would equal the mean of the population, right? What would be the shape of it? Well, since it's small, it's not going to be normal yet. So I don't think that, and because the original population was skewed. If the original population was normal, I could go ahead and just choose those, even though n is small. But I think we're going to choose one of these. These are all the same. So let's look at these and see which one, what happens. Now, as sample size, which is following true about the shape, center, and spread of the sampling distribution. So when you take a sampling distribution, it's going to immediately start getting smaller. Remember, we've done that even with our pennies and nickels, and remember we started to, I don't know what exactly this will look like, but it'll have a smaller spread to it. The sampling distribution may look something like that, maybe not quite as spread out as this one is. So certainly we do know this, that the standard deviation of the sampling distribution would be smaller than the population. Now let's just double check we're right. Yes, A is correct. And it says some things there you can read. Number 10. So a young woman works 2 jobs and receives tips from both jobs. As a hairdresser, her distribution of weekly tips has a mean of 65, standard deviation 575, so those two go together. And then the other job, mean of 154, and standard deviation of 8.02. what are the mean and standard deviation of our combined weekly tips? So assume an independence for the two jobs. So we're treating these as independent random variables. When you add up the means, you literally just add up the means. 65 plus 8.02. Mean of 154, sorry. And a mean of 65. So what's 154 plus 65? That would be 219, so it's one of these. And then when you do standard deviations, when you add standard deviations for independent random variables, you can't just add them. You got to deal with the variance. You got to take the square root of 5.75 squared plus 8.02 squared. You got to add their variances basically. Whatever that is, I think when you do that, you get 9.87. So that would be the correct answer. It would be D. But that's how you do that. You got to remember when you add, the means add just normal, and the standard deviations don't. Okay, it's been a while since we mentioned cause and effect, and we still don't know how to really prove this yet all the way, but we do know that there are certain things that can have a cause and effect that a study or something we can prove that study. So, this is not just a correlation, but actually a cause and effect. A survey conducted using a simple random sample, that's not good enough, will not actually do it for us. Survey conducted using stratified, again, still not good enough. Correlation near 1 or -1, that may prove some correlation, but does not prove cause and effect. Observational studies certainly can't be cause and effect. Here's the key. An experiment, it must be an experiment. I think it always has to have a control group. It always has to be controlled for sure. Where the observations are assigned randomly. So it must be an experiment to be cause and effect. We have learned that, and that's as much as I expect you to know about cause and effect at this point in time. Which of the following is not a condition for geometric? It's been a while since we've done geometric. The big thing I wanted you to remember from geometric is, anytime you want first successes, that's one of the requirements. You're looking for the first time you roll a 5 or first time you pick an ace or something like that. Certainly some of the conditions are there are only two possible outcomes. That's called the Bernoulli trial. The probability of success is the same. That's important. It doesn't change. The trials are independent. Certainly we need independence. This is one of the conditions, but this is for binomial here. So I believe this one is for binomial, not for geometric. You have to have a fixed number of trials for binomial, which is, you're maybe going roll for a 2 to a 5, or let's see, we'll come up with some examples of binomial which are a little different. We're not looking for the first success. We're looking for where there's only two options, but from 2 to 5 or something like that. It's a little different for binomial. And for a set of values, the mean is 10, standard deviation is 2. Each value is multiplied by 9. So when you multiply by 9, interestingly, the mean is multiplied by 9 and the standard deviation is multiplied by 9. So the correct answer there is E, 90 and 18. So when you add, you have to be careful of standard deviation, but multiply is the way you would think it would do it. In a game of chance, 3 fair coins are tossed at the same time. If all 3 coins show heads, by the way, the probability of that happening would be 1 out of 2 times 1 out of 2 times 1 out of 2, which is 1 out of 8. You would get 3 heads. You get $15 if that happens. If all 3 coins show tails, again, 1 out of 8 probability of getting all tails, you get $10. That's pretty good. And the rest of the times you get $5. You have to pay $5. So the expected outcome here would really be 1/8 times 15 plus 1/8 times 10 minus 6/8 times -5, or times 5, I should say.